Thank you very much. Well, thank you very much for joining and listening my lecture in such a difficult time. Thank you. Now, let me share my slide. Okay, so can I start?
Yeah, sure.
Okay, well, today I want to talk about neutrino oscillations and small neutrino mass. Now, this is the outline of this talk. First, I have a brief introduction on neutrinos. Then I want to discuss the early days of the neutrino oscillation studies. Then I want to move on to the discovery of neutrino oscillations, solar neutrino oscillations. And before finishing this talk, I want to discuss the importance of small neutrino mass. And I'll summarize this talk. Okay, what are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons without electric charge. And in fact, this has a profound impact. Neutrinos can easily pass through even the Earth, but they can interact with matter very rarely. And therefore, it is possible for us to study neutrinos. And neutrinos have, like the other particles, three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And neutrinos have been assumed to have no mass. However, small neutrino mass might have profound impact to our understanding of elementary particles and the universe. Therefore, people have been eagerly searched for the finite neutrino mass. And finally, neutrinos can be detected. For example, by this way, neutrino interact with a nucleus, then typically a particle, charged particle is emitted. Then, of course, we have various ways to detect this charged particle. And for example, if this nucleus is a water nucleus, then this charged particle propagates in the water. Then in this case, Cherenkov photons are emitted. And therefore, if we detect these photons, we can identify the neutrino interaction. And this way, we study neutrinos. Now, I want to move on to the early days of the oscillation studies. And first is the solar neutrinos. As you know, the sun generates energy by nuclear fusion processes. During these processes, many neutrinos are generated. Therefore, people thought if we observe solar neutrinos, we can understand the details of the energy generation in the sun. So, more than 50 years ago, the Homestake experiment, which is shown in the middle of this page, observed solar neutrinos for the first time. This was great observation. This experiment confirmed the energy generation mechanism of the sun. However, the observed event rate was only about 1/3 of the prediction. So this was an unexpected result, and people were unable to explain what was the cause of the deficit. Anyway, people called this problem as solar neutrino problem. Now, following the initial observation, several experiments observed solar neutrinos in the 80s and 90s. And here I summarize the solar neutrino results as a function of the threshold energy, and the vertical axis is a ratio to the standard solar model prediction. So if the observed data are consistent with the standard solar model prediction, data points should be consistent with this line unity. However, all the experimental data indicated a significant deficit compared with the theory. So solar neutrino experiments in the 80s and 90s confirmed the deficit of solar neutrinos. But around that time, we were unable to identify the reason for the deficit. Now I want to move on to the next topic, that is the proton decay experiments. In the 1970s, grand unified theories of elementary particles predicted that protons should decay with a lifetime of about 10 to 30 years. But the idea of grand unified theories were very important. They predicted that three completely different forces should be unified at the very high energy scale. And if we observe proton decays, that proves the idea of grand unified theories. Therefore, several proton decay experiments began in the early 80s. And here I show the experiments that started the experiment in the 80s, early 80s. From the left to the right, KGF, NuSex, IMB, Camiocanda, and Frejus. These experiments wanted to observe proton decays, but unfortunately, they didn't observe any proton decay. Instead, these experiments observed background events to the search for proton decays. And the most serious background to the search for proton decays were neutrino interactions. And these neutrinos are created by cosmic ray interactions in the atmosphere. Cosmic ray particles, once enter into the atmosphere, interact, with the air nucleus, then typically pions are created. Of course, pions are unstable. They decay to muons and then to electrons. And during this decay chain, neutrinos are created. And of course, most of these neutrinos simply pass through the Earth, but some of them interact in the proton decay detector. And therefore, people have to carefully analyze these events in order to separate proton decay signals and the neutrino backgrounds. Anyway, proton decay experiments in the 80s observed many atmospheric neutrino events. As I discussed, because atmospheric neutrinos are the most serious background to the proton decay searches, it was necessary to understand the atmospheric neutrino interactions. And during these studies, a significant deficit of the atmospheric muon neutrino events was observed. And here I summarized the results from Camiocanda and IMB experiments. These experiments observed significant deficit of the muon neutrino events in the data as compared with the prediction by the Monte Carlo simulation. So again, if the data are consistent with the theory, the data point should be consistent with this line at 1. However, both experiments observed significant deficit of muon neutrinos. Again, in these experiments, this kind of data were observed, but they were unable to identify the reason for the deficit. Well, it's true that these experiments were unable to identify the reason for the deficit. People discussed various possibilities. And one of the possibilities was the neutrino oscillations. Well, neutrino oscillation was theoretically predicted by these people, Maki, Nakagawa, Sakata, and Pontecorvo. And according to them, if neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, mu neutrino could oscillate to tau neutrinos. And let's suppose that a mu neutrino is created at this point and begin to propagate to the right. Then at some point, the probability that mu neutrino to remain as mu neutrino goes down. But if they propagate further, the probability come back to unity. If they propagate further, the probability goes down once again, then come back to unity, and so on. And when the mu neutrino disappeared, then tau neutrino is appearing. So this is neutrino oscillations. And of course, if this is occurring, then one can naturally explain the deficit of muon neutrinos in atmospheric neutrino experiments or proton decay experiments. Now, I'd like to move on to the discovery of neutrino oscillations. Well, the neutrino oscillation was discovered by Super Camiocanda. And Super Camiocanda is a much larger version of the original Camiocanda experiment. Super Camiocanda is a 50,000-ton water Cherenkov detector located 1,000 meters deep underground. It has about 40 meters in diameter and 40 meters in height. And this is about 20 times larger than the original Camiocanda experiment. And by the way, this is an international collaboration. We have about 200 collaborators from 10 countries at this moment. I just want to show you two photos during the construction of the Super Camiocanda detector. This photo was taken in the spring of 1995 when we constructed the Super Camiocanda detector at the bottom of the Super Camiocanda tank. So at that time, these many people worked at the bottom of the Super Camiocanda tank, and about, I would say, 70 to 80% of these people are physicists, Super Camiocanda collaborators. So at that time, we worked in underground to construct the Super Camiocanda detector. Well, in fact, the construction work went well. And in January 96, we started to fill in the detector with the pure water. This photo was taken from the top of the Super Camiocanda detector, viewing inside. And you can clearly identify the water level as you identify the plastic boat. Anyway, the experiment started from April 1996. And from the beginning of this experiment, we observe these events. And this is a typical mu-neutrino event observed in super K. So, well, here the cylindrical detector is cut and open flat. And you see many small dots or circles with colors. And the size of the dots or circles indicate the photon intensity that was observed by each photodetector. Also, the color of these dots or circles indicate the photon arrival timing. So Super Camiocanda observes about 10 neutrino events in a day. And we formed a team to analyze these events. Well, I said in the previous generation experiments, people observed a deficit, but people were people were unable to identify the cause of the deficit. Now, in Super Camiocanda, we thought we have to identify the cause of the deficit. And for this, we thought this way. Well, first of all, neutrinos are created in the atmosphere. Therefore, some of these neutrinos are created above the Super Camiocanda detector, typically 10 to 20 kilometers above Super Camiocanda detector. And these neutrinos, after traveling 10 to 20 kilometers, come to the detector and interact. And these neutrinos, since these neutrinos only travel 10 to 20 kilometers, these neutrinos may have no time to oscillate. On the other hand, neutrinos are created also created in the other side of the Earth. And these neutrinos have to travel long distances, typically 10,000 kilometers. Therefore, these neutrinos have to have enough time to oscillate. So if we think this way, we can easily expect that we should observe the up versus down asymmetry of the atmospheric mu-neutrinos. However, the problem is the number of events. The previous experiments were too small to observe this effect. Therefore, a much larger detector was necessary, and therefore, Super Camiocanda was an ideal detector to observe this effect. So we analyzed the data carefully, and finally, in 1998, we showed our analysis result at the Neutrino conference. Here, I copied one of the slides we presented at the Neutrino conference. Here, we show the Zin's angle distribution for electroneutrinos and mu-neutrinos. And the horizontal axis is the Zin's angle. Cosine theta 1 means downgoing neutrinos, -1 means upward-going neutrinos coming from the other side of the Earth. Then black circles with dead error bars show the data, and the hatched histograms show the theoretical prediction, but without oscillations. Then we see that for electron neutrinos, the data and the prediction agreed, more or less agreed. On the other hand, for mu-neutrinos, and in particular, for downgoing neutrinos, data and prediction agreed. However, for upward-going neutrinos, the data showed almost a factor of 2 deficit. And this can be naturally explained if we take into account neutrino oscillations, namely mu-neutrinos created in the other side of the Earth. oscillate while propagating inside the Earth. And therefore, when they come to the super Camiocanda detector, the probability that muon neutrino is remaining as muon neutrino is just 1/2. So this way, we discovered neutrino oscillations. Of course, we reported our result at the conference for physicists. However, well, I think we were extremely lucky. Something unexpected happened. President Clinton of the United States gave a talk at MIT's 1998 commencement. And in fact, his talk is still available on YouTube. But anyway, let me repeat what he said. Well, this was just in the middle. Anyway, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works, and indeed, how it expands. Then he continued, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. Well, I think we are really honored to hear this kind of words from the US president. Now, I'd like to discuss this second oscillation discovery, that is the solar neutrino oscillations. The main detector, main experiment that contributed to understand the solar neutrino problem or to confirm the solar neutrino oscillation was the snow detector. The snow detector was located 2 kilometers deep underground. And it is a 1,000-ton heavy water detector. And heavy water is contained in this container here. And because of the use of heavy water, they can observe the electron-neutrino interactions. Therefore, they can observe the electron-neutrino flux. In addition, they can observe the neutrino interaction that is independent of the neutrino type. So this way, independently, they can observe the total neutrino flux. The result is shown here. If they observe the electron-neutrino flux, then the observed flux was just about 1/3 of the prediction. However, if they observe the total neutrino flux independent of the neutrino type, then the observed flux was just as expected. And the sun can only generate electron neutrinos. The result clearly indicates that neutrinos change type somewhere between the center of the sun and the Earth. And therefore, this was the evidence for solar neutrino oscillations. And because of this achievement, Art McDonald received the Nobel Prize in Physics in 2015. Now, I'd like to move on to the importance of small neutrino mass. Well, you may wonder why we are so excited with the small neutrino mass. Well, quarks have mass, charged leptons have mass. Therefore, in a sense, it's natural that neutrinos have mass. However, we still think that small neutrino mass are very important. And I'd like to convince you by simply showing the mass of these neutrinos. The mass of the neutrinos are shown here. Then you notice that neutrino mass is much smaller than the mass of quarks and charged leptons. And in fact, the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude smaller, very small. And we believe this is the key to better understand elementary particles and the universe. Therefore, we are excited. Well, certainly, if we understand why neutrino mass are so small compared with other particles' mass, then we think we understand the elementary particles better. But we think this understanding is related to the understanding of the universe. Why? Well, let me explain. This is the photo of the far universe taken from the net. And you see many stars and galaxies. And we know that these stars and galaxies are made of matter particles. We know that there is no antimatter star or antimatter galaxy. Well, it seems this is just natural, but well, too trivial. But well, if we think about the Big Bang universe, this is non-trivial. In the Big Bang universe, the temperature of the universe was extremely high. And in this Big Bang universe, particles and antiparticles were always created simultaneously. Therefore, in the Big Bang universe, we naively expect an equal number of matter particles and antimatter particles. Then, with the universe cooled down, particles and antiparticles meet and annihilate, disappear. So, therefore, we naively expect there should be no matter particles, no antimatter particles in the present universe. However, of course, we know that there are many matter in the universe, in the present universe. In fact, I think we understand the mechanism pretty well. In the very hot Big Bang universe, the number of matter particles was, say, 1 billion 1. And on the other hand, number of antimatter particles were 1 billion. They were almost equal. Then, with the universe cooled down, these particles and the antiparticles meet and annihilate. And therefore, at present, we have this one particle coming from this extra one. So this is us. This way we understand. However, 1 billion 1 is almost equal to 1 billion, but they are not exactly equal. Therefore, we should be able to explain why there was extra 1 in the matter side. Well, to be honest, we do not know the reason. However, many people are thinking that neutrinos with very small mass might be the key to understand this big mystery of the matter in the universe. Well, certainly this is a very important idea. However, of course, we are physicists. Therefore, we have to test this idea experimentally. And we think that we should study more on neutrino oscillations. And we'd like to, in fact, we'd like to observe if oscillation of neutrinos and those of anti-neutrinos are different. And if we observe this difference, it will be the first step to understand the origin of the matter in the universe. So we should observe this effect. However, the present generation neutrino experiments are not powerful enough to observe this effect. Therefore, we need the next generation long baseline experiments with much higher performance neutrino detectors. And in fact, there are two large projects going on. One is the DUNE project in the United States. Another is the Camiocanda project in Japan. Both are international projects. But since I'm from Japan, therefore, in the next page, I'd like to explain the Camiocanda project a little bit more. Well, Camiocanda will be an extremely large water Cherenkov detector. It will be about 70 meters in diameter and 70 meters in height. The total, the fiducial mass that can be used for the physics analysis will be about 8 times larger than the present super K. And because of this very large mass, we expect many important research topics in neutrino physics and astrophysics. And this project has been approved by the Japanese government about 2 years ago. So the construction started in 2020, and we expect the experiment will start in 2027. And I want to mention that Camiocanda is again an international collaboration, in fact, a very large international collaboration. We have about 500 members from 20 countries, and including, of course, Ukraine. And well, in order to show you how the construction is going on, I simply show you a photo of the entrance tunnel. So the excavation of the 1.9 kilometer long access tunnel to Hyper-K has been completed in February this year. Okay, now before finishing, I'd like to show you one slide. This is the message by the President of the Science Council of Japan. Well, this message was issued on February 28th this year, a few days after the Russian invasion of Ukraine. So, well, we issued this issue and we issued this message, and let me read. The Russian invasion of Ukraine threatens international peace and security and undermines the very foundations of the international order. This is unacceptable. We are deeply concerned about the impact of this situation on people's peace and safety, as well as on the development of the sciences and international cooperation in the sciences in Japan and the world. We honestly hope that a peaceful solution through dialogue and negotiation will be reached. Okay, let me summarize. Neutrinos are very interesting particles. Neutrino oscillations and therefore small neutrino mass were discovered by Super Camiocanda in 1998. Small neutrino mass is very important for the better understanding of elementary particles. And small neutrino mass might also be the key to understand the fundamental question of the universe. And neutrinos will continue to be very interesting. We are looking forward to working together with our Ukrainian colleagues in the Hyper Camiocanda project. And finally, I sincerely hope that peace will be restored as soon as possible. Okay, that's all from me.
Thank you very much, Professor, for your masterclass. We have many questions to you in different topics. Actually, I will read out, first of all, questions about the research and the topic of your lecture. So the first question is from Mykola. How do you differ atmospheric neutrino apart from the solar ones in the super Camiocanda detector?
Okay, thank you very much. Well, first of all, the energy is quite different. Solar neutrinos are created by nuclear fusion processes. Therefore, these neutrinos are in the MeV range, actually 10 MeV range, 10 million electron volt. However, atmospheric neutrinos are created by high energy cosmic ray interactions in the atmosphere. And therefore, the typical neutrino energy is GeV 10 to 9 electron volt. So about 2 orders of magnitude difference. Therefore, it's very easy to separate these two neutrinos. That's all, okay.
Okay, the next question is from Yuri. How exactly was it discovered from neutrinos exist in the first place?
Oh, how we discover neutrinos for the first time? Yeah, okay, thank you. In fact, well, neutrinos were actually theoretically conceived nearly 100 years ago. Well, I think about 90 years ago. At that time, people observed nuclear beta decays. And well, in nuclear beta decay, beta ray is emitted and the nucleus is converted to other nucleus. And if this is everything, then the energy of the beta ray should be always equal, a fixed number. However, people observed that beta ray energy is continuous. This was a big mystery, and therefore people thought that during the beta decay, in addition to the beta ray, there must be some invisible particle emitted. And this is neutrino. So this way, the initial idea of neutrino was proposed.
Okay, the next question is from Elizaveta. What's the difference between neutrino and anti-neutrino?
Oh, thank you. Well, okay, so certainly I didn't explain well, I said that if there are matter particles, always there should be antimatter particles. And therefore, same is true for neutrinos. We have neutrinos, and therefore we have their antiparticle, anti-neutrinos.
Okay, and related question, have you recorded anti-neutrinos? Yeah, I understand that you said yes. The question from Mykola, has an aneutrinon has been recorded?
Excuse me?
Has anti-neutrino has been recorded?
I see anti-neutrinos recorded in Super Camiocanda already?
Yeah.
Yes, yes. We have already observed anti-neutrinos in Super Camiocanda, yes.
And the next question is whether it is possible to accelerate neutrino to the speed of light.
Say again.
Whether it is possible to accelerate neutrino to the speed of light.
Oh, okay. Now we know that neutrinos have mass. The mass is small. Therefore, the speed of neutrinos should be very close to the speed of the light. However, because of the mass, the neutrino velocity cannot be equal to the speed of the light. Okay?
Okay, the next question from Mikhailo. If neutrinos are involved in a weak interaction, then which particles bind neutrinos?
Which particles?
Bind neutrinos, some connect neutrinos.
Oh, which particle is connected to neutrinos?
Yeah.
I see. I see. Well, thank you for this question. If say, well, let's suppose here is an electron neutrino. Then if an electron neutrino interact with the nucleus, then electron is produced. In this way, electron neutrino is connected to an electron, a muon neutrino is connected to a muon, and tau neutrino is connected to tau particle. Okay.
The next question is from Maria. What experiments were performed with neutrino in different detectors in 2020-2021?
In 2020 and 2021, I see. Yeah, okay. At present, there are two large accelerator-based long baseline experiments going on. One is the T2K experiment. This is the experiment carried out in Japan. The neutrino beam is created at the J-Park accelerator complex, and the neutrinos are detected in super Camiocanda. The baseline length is about 300 kilometers. Another large neutrino oscillation experiment is NOVA in United States. Neutrinos are created at Fermilab, and these neutrinos are detected at the NOVA detector, which is located about 800 kilometers downstream of the production point.
Okay, the next question is from Yevhen. Is it possible to accelerate neutrinos and control their trajectory, like electrons in synchrophasotron?
Thank you for this question. Well, okay, as far as I know, I think, well, I have no idea to accelerate the existing neutrinos. Well, in order to accelerate particles, we typically use electromagnetic force. However, neutrinos are neutral, electrically neutral. Therefore, I cannot imagine how to accelerate the existing neutrinos.
Okay, the next question is from Makola. Can each neutrino interact with a proton? Does it take energy?
Well, certainly a neutrino can interact with a proton. Then certainly during this interaction, a fraction of the energy is transferred to the nucleon side. Typically, neutrinos lose their energy and the nucleon side gets some energy.
Okay, the next question is from Veronica. Is there any new information about the particle of dark matter? Is a connection between neutrinos and dark matter possible?
Oh, thank you very much for this question. Well, in fact, maybe about 30 years ago, people thought maybe neutrinos are dark matter particles. However, first of all, the discovered neutrino mass was a little bit too small to be the main component of the dark matter. Also, people realized that the small neutrino mass cannot, suppose, even if we suppose that neutrinos are dark matter particles, these small neutrino mass cannot explain the structure of the universe. Therefore, people think that some other particles, typically heavier particles, are necessary to explain the structure of the universe. So we think neutrinos are not the main part of the dark matter.
The next question is from Mikhailo. So somebody says that there is some antimatter left in the universe, and it helps explain gravitational effects. If this is so, why is this antimatter not destroying this with the matter?
Mm-hmm. Could you repeat?
Okay, I will repeat. Somebody says there is some antimatter left in the universe, and it helps to explain gravitational effects with gravitation. So if this is true, why is this antimatter not destroyed with is not destroyed with this matter?
Well, okay. Well, to be honest, I don't know what kind of theory you are mentioning. Mm-hmm. But as far as I know, antimatter particles are only observed. Well, certainly the fraction of the antimatter particles are very small. In fact, in cosmic rays, we observe antiprotons, but with the fraction very small. And therefore, I don't know if there is any kind of evidence for antimatter in a large scale. I'm sorry, I don't know.
Okay, the next question is from Serhi. How and into what particles does a neutrino decay?
Neutrino decay, oh, yeah. I see. Well, I'm sorry. I have no idea. Well, certainly neutrino lifetime must be very long. Therefore, you have to extremely carefully design your experiment or observation in order to see the finite neutrino lifetime. I have no idea.
Okay, the next question is from Yelizar. Why super and hyper Camiocanda detectors are so big?
Oh, I see. I said that we'd like to observe the difference of the oscillations between neutrinos and anti-neutrinos. And we expect this difference is small. And in order to observe the small effect, you need high statistics. And in order to get high statistics, you need very intense neutrino beam and very large neutrino detector. So therefore, hyper-Camiocanda is this big.
Okay, the next question is from Maria. What can you say about creation of Cherenkov detector? Maybe you heard about it.
Oh, okay. If a relativistic particle propagate in a medium, then as a kind of shock wave, generation, Cherenkov radiation occurs. Well, maybe this is all I can say.
Okay, the next question is about motivation overall. So what can you advise modern school students who want to do research and science?
Well, certainly science is extremely interesting. If you are interested in science, I certainly advise you to try to be a scientist. And in fact, well, I have been very happy to be a scientist. I was always inspired by various scientists, and this is really exciting. So, well, I'm sorry, maybe I cannot answer properly, but certainly to be a scientist is very unique, very important.
Okay, the next question is from Yuri. Would it possible to find out solar neutrino among distant stars in the future?
Oh, thank you. Well, certainly, solar neutrinos from the other stars could be a possibility, but well, okay, that is certainly a possibility, but unfortunately, the other stars other than the sun are, in my opinion, too far away. Therefore, I cannot be so optimistic, but maybe I'm wrong. Anyway, other stars could generate neutrinos. For example, at the end of the life of the stars, there's a big explosion. This is supernova. And during the supernova explosion, many neutrinos are created. And certainly these neutrinos could be observed. And if we observe this kind of neutrinos, it will be certainly very important for the understanding of the supernova explosion.
The next question is from Andrei. Neutrino accelerates a particle that is affected by beta decay. Is it the only way to accelerate neutrino?
Well, okay, certainly, as I said, electromagnetic forces are useful to accelerate neutrinos. Therefore, in order to get the energy of a neutrino, they have to be created by beta process, beta decay, or some other processes, weak interactions. And what was the question?
Okay, the next question is from Mikola. Do neutrino stars emit neutrinos?
Neutrino stars?
Yeah.
Well, first of all, well, okay, neutrino stars. In fact, this is a very interesting question. Well, a few minutes ago, I briefly mentioned the supernova explosion. And during this explosion, neutrinos are created. Many neutrinos are emitted. But, well, in a sense, the supernova, at the center of the supernova, the dense star is almost like a neutrino star. Of course, neutrinos are only a part of the central part of the star, but there are so many neutrinos at the central part of the star. So in a sense, supernova explosion is a kind of neutrino star.
Okay, the next question is very long. I will read it slowly. So, whether neutrinos can affect the process of expanding the universe? If the lifespan of neutrinos is very long, it turns out and they are becoming more and more. And if there is an effect of neutrinos on the expansion, it turns out that when neutrinos begin to decay, the expansion can slow down or stop the expansion.
Okay, thank you. Well, certainly, neutrino mass is, in a sense, sensitive. Well, okay, this way. The universe expansion is certainly controlled by various factors, and one of the factors is the neutrino mass. And well, neutrino mass is very small. Therefore, at present, we think that neutrino mass will not largely affect the universe expansion. Furthermore, I think neutrino lifetime is much longer than the age of the universe. Therefore, the effect of the neutrino decay can be neglected, I think. Maybe I'm wrong.
Okay, the next question is from Kirill. Does it make sense to try to study neutrino outside the Earth? So will the result be the same?
Oh, thank you. In fact, this is quite interesting. Well, today I discussed neutrino oscillations. In fact, we know that how neutrinos oscillate depends on the material that neutrinos have to travel. Well, of course, they have to travel very long distances in order to see a visible change in the neutrino oscillation probability. But therefore, in principle, if we carry out another experiment, some other planet, then the data, comparison of the data taken in the Earth and the other planet could be interesting.
Okay, do you expect a big breakthrough in physics in the nearest future? What it will be, in your opinion?
Oh, breakthrough in physics. Oh, thank you. Well, okay, well, I want to stick to the experiments I explained in this talk. I discussed hyper-Camiocanda, and it will be a very large detector. And also at the beginning, I mentioned that in the early 80s, there were many proton decay experiments, and they didn't observe any proton decays. And we are still continuing the search for proton decays. And certainly in hyper-Camiocanda, we should continue the search for proton decays. And if the proton decay is observed, that is the direct evidence for the unification of elementary forces. That is really a breakthrough.
Okay, the next question is from Makola. Is there existence of neutrinos related to gravitons, which are only theoretically predicted?
Well, okay. Graviton.
Yeah.
Well, okay. I believe the existence of graviton, but I have no idea how to experimentally confirm the existence of graviton. I have no idea.
Okay, now I will ask some overall questions about your motivation. So what project are you working currently on?
At present?
Yeah.
Yeah, well, okay. I'm currently working on a gravitational wave project. This is laser interferometer experiment. We have constructed 3 kilometer by 3 kilometer laser interferometer. This is a very high sensitive interferometer to observe gravitational waves, but we are not ready yet. We hope we are ready by the end of this year.
We will hope as well. The next question is, what inspires you to make science? Why did you become a scientist? How you understand that you want to do science and research?
Well, certainly, I wanted to understand the nature, universe, or elementary particles, whatever. I wanted to understand the nature better. That was the only motivation for me to become a scientist. And in fact, I'm very happy to be a scientist.
Okay, and we have many questions left, but unfortunately we have some limitation in time. So I will close this discussion by one very prospective question. What is the most important item to become a successful scientist?
Okay, thank you. I think you have to have strong interest in science or universe or whatever.
Okay, thank you very much for your presentation and your masterclass and your strong position and clear position in our situation. Thank you very much again, and have a nice day and good luck. And I'm waiting for you to come to Kiev again after,
thank you very
after
much.
the war.
Yeah, well, certainly, I hope that peace will be restored as soon as possible. Thank you very much for the invitation today. Bye-bye.
Thank you very much. Шановні учасники, дякую, що приєдналися до нашої чергової лекції. Наступна лекція, нагадую, відбудеться 27 квітня. Будь ласка, реєструйтеся за посиланням, які ви знайдете на нашому сайті. Thank you very much. Have a nice day. Всім дякую і гарного дня. Goodbye.
Okay, thank you. Bye-bye.